Okay, so this video is going to be on refraction. All right, this is part of Unit 8. You should have these guided notes right here in front of you. Now, the speed of light, we know, is 3 times 10 to the 8th meters per second. That's how fast light moves in a vacuum. Now, that doesn't mean light moves that speed all the time. You know, a vacuum is in the absence of any medium or any dense medium. It's like it's traveling through air. All right. Now, when a light ray if it's to hit water, it's going to slow down. Or if it hits or if it comes from water into air, it's going to speed up. So the speed of light will be different in different mediums. However, when light travels through more dense materials such as water, the light will slow down and it will bend. And this bending is actually what refraction is. Now, we talked about reflection. Reflection is like when light bounces off a surface and reflects back. That's different than refraction. Now, that's like when in a mirror, how light hits it and bounces back. And according to the law of reflection, whatever the angle that the light ray hits the surface of something, it's going to reflect at the same angle. So if it hits at 40 degrees, it's going to bounce back at 40 degrees. Now, refraction is different. Now, one thing about light, when it hits a new medium, its frequency does not change. All right, therefore, the speed of a wave is directly proportional to its wavelength. You need to know that. That will be a test question. Frequency does not change. So if a light wave slows down, then its wavelength gets shorter. Now, refraction is the bending of light and the change of direction of a wave due to the change in speed at the boundary between two different media, such as air and water. The wave must travel obliquely at an angle. Now, to look at refraction, if you notice this little simulation right here if you notice this light, it's like these red lines here, they are hitting this boundary and the angle of incidence, the first angle there that hits that is 25 degrees, and then it's refracted, it's bent at 49.5 degrees, and that's from going from air into water. Now, if we change this angle, the sense of that angle, the angle of refraction that refracts, that's going to change. If we change it to 15 degrees, it changes. If we change it to 10 degrees, it refracts, at a lower angle. And then at 5 degrees, it's going to refract at 9 degrees. And then if you notice though, if there is no angle and it's going straight down, the light does not refract. So it has to be hitting at an angle. Now, if you look at this diagram, there's some different concepts here that we need to know. That angle tells you that, this first light ray here is what's called our incident ray. And this angle right here is the angle of incident, and we usually say that's theta. All right, and then we have, then when it bends, we have our refracted ray right there, and it has an angle of refraction. That is what we call that theta R, and we call the incident angle theta I to distinguish between the two. And then if you see, there are some other numbers here. We have an index of refraction, which is N1. And that's the index of refraction for the first medium. And what the index of refraction does is tell you, it's kind of a number with no units that tells you how dense the medium is. So air is going to have a lower index of refraction than water, and something like diamond is going to have a higher index of refraction than water or air. Now these values I would have to give you in the problem, or supply you with a chart that has those values, or we might calculate those. Just depends on what our problems give us. Now this is called actually the absolute index of refraction. Now usually you'll hear me just talk about the index of refraction, so I'll leave out the absolute. And that's the ratio of the speed of light in a vacuum, and the symbol for the speed of light is C. To the speed of light in the material medium. That's how fast it's moving in the whatever medium it's traveling in. And like I said, it has no units. And the equation for that, for the N values, the index of refraction, is equal to the speed of light in a vacuum over C over V, which is the speed of light in whatever material it's traveling in. Now, with this equation, we will not work any problems with that, but just to show you, on a diagram or a simulation, I can, you see these different at the bottom here, say our top substance, that's our, going to be our N1, our first medium, and I have different ones. Let's say if I select air, my first medium is air. If you notice, it has an N value of 1.0003, which is pretty much 1.00. My second substance, I'll select my bottom substance, my N2, that's water. If you notice, its N value is going to be 1.33, which is higher. That makes sense because it's more dense and light isn't going to travel as fast. So if a light ray is moving from air to water, it's going to refract, especially at a certain angle. So if we do that, if we notice that it hits right here, and there's going to be some reflection. If you notice, some is reflected back out at the same angle at which it hit the surface, but then some's going to be refracted. It's going to be bent, our line that keeps going through the water there. Now if you notice, this index of this angle would change if I was to change the angle at which it hits. Now there's going to be a point where none will refract. Now as long as I'm at an angle, but if I keep moving up at a certain point, there's still refraction there. If I get to here, there's still refraction. And here, light no more is refracted, or reflected. Now, if I change the substance, let's say if I make the top substance water and the bottom substance air, if you notice, in that case, it was just reflected. That case also. But then at that angle right there, angle is refracted. Now if I made the top substance, let's say air, and the bottom substance diamond, and we look, angle is refracted. Now I can show the way we measure these angles. If I have a protractor and I put it right there, I notice that the angle at which and I'll just do another one, say that angle right there for measuring my protractor is about 41 degrees would be the incident angle, and then it's refracted if I measure it, and actually that dotted line down the middle is what we call the normal line. It's drawn perpendicular to the boundary at which a light ray in between two medium. It's always drawn perpendicular, and I measure my angle in between the light ray and the normal line there. So my incident angle in this case would have been like 41 degrees, and it was refracted at about 17 degrees right there. Now one thing is, this is moving from a medium where light travels faster, and then it's going to slow down as it moves through the diamond. If it moves from where it's going fast to where it slows down, into another medium to where light slows down, it's going to bend towards the normal. Now if I was to change these two, and put diamond on top and air on the bottom, and then do this again, my incident angle is the same, but in this case none was refracted. You know, I'd have to actually change my angle, and in that case it wasn't. Since this is such a big difference in the end values, it takes the angle. In this case, if you notice that the incident angle is about 15 degrees, the refracted angle is about 41 degrees. All right, so if it's moving into it from a medium to where light travels slower, and then light's going to speed up, that refracted angle there, the light ray is going to move away from the normal. And if I, like I said, if I try to swap these and put air on top and diamond on bottom and do this again, in this case, it's moving from a medium to where the speed is going to slow down because it's moving from air into diamond. If you notice that the refracted angle is a lot lower, and so the light ray is going to bend towards the normal line there because the angle is a lot less. My refracted angle in this case would have been about 7 degrees. All right, so if we look back at our notes, every material has an index of refraction. The more dense a material, the higher the index of refraction. And that's because it's harder for light to move through there. Light's going to slow down. And we usually have a reference table for these. Now, M1 is going to be the index of refraction for the first medium that light's traveling through. N2 is going to be the index of refraction for the second medium. Now, Snell's law is the mathematical relationship that governs the refraction of light. So it's our equation we're going to use for refraction problems. That equation right there. It's N1 times the sine of theta 1, which we usually call theta I. So make that change. That's my incident angle, my first angle. And then equals N2 times the sine of theta. Instead of theta 2, change that to theta R. That way it will be our refracted angle. So N1 is the index of refraction of the first medium. N2 is the index of refraction for the second medium. Theta 1, which change that again in your notes to theta I, that's my angle of incidence. And then theta 2, we could change to theta R, that's the angle of refraction. So the light will bend either away from the normal or towards the normal. That's what we just talked about in simulation. If light travels from a less dense medium, which is a fast medium, which light travels fast, to a more dense medium, it's a slow medium, the light will bend towards the normal and the speed of the light ray will decrease. It's very important that you memorize this. These will be test questions. If the light travels from a more dense medium, where light travels slow, to a less dense medium, or a fast medium, speed of light's going to increase and the light ray will bend away from the normal. So you need to memorize those. So let's look at some Snell's law problems. Well, these are actually just questions first. If light travels from air, which has an N value of 1.00, to glycerol, where N equals 1.47, will the light bend towards or away from the normal? Well, it's moving from a medium where it's traveling fast to where it slows down. So it's going from a less dense medium of air to a more dense medium in glycerol. So, like I said, it's going to bend towards the normal. If light travels from glycerol to water that has an N value of 1.33, and we know that glycerol is 1.47, will the light bend towards or away from the normal? So in this case, it's going from a more dense medium to a less dense medium, so the speed of light is going to increase and it's going to bend away from the normal. Now, for Snell's law problems, this is problems we'll be using our equation. It's just like all the other equations we used this year. You are going to be given givens in the problem. You can be solving for an unknown, and using the equation. So we're going to use the guess method like we always do. So it tells us in this problem that a light wave in air, and it tells me that my n value for air is 1.00, and I'll have to give you that value or give you a table with it in there for those values, and thus we're solving for them. And it enters water, so water is going to be my second medium, air is going to be my first medium, and it says it enters water at an angle of 30 degrees. So what is that angle? The angle of refraction or the angle of incidence? Angle of incidence is always the angle that my first medium that the light ray travels through, and the angle it strikes the boundary. And the angle of refraction is going to be my second one. It tells that it enters water at an angle of 30 degrees, so that's giving me my theta I. And it's asking me to determine the angle of refraction. So it's telling me what I'm solving for. So if I write down my givens and my unknown, I know that my N1, that's my N value of the first medium, is going to be 1.00 because air is my first medium. My N2 is going to be 1.33 because that's my second medium is water. And it's an angle. My theta I is going to equal 30 degrees. And then I'm solving for theta R. That's my unknown. Okay, next I need my equation. My equation is this one, N1 sine of theta I equals N2 times the sine of theta R. Alright, so I'm going to plug in now. I'm going to plug in my numbers, and I'm going to substitute and solve. So N1 was 1.00, and that's times the sine of theta I, which is 30 degrees. That equals N2, which is 1.33, and then it's times the sine of theta R. Alright, so I'll get my calculator. And I take, make sure that you're in degrees when you work these also. I take 30, I'm going to take the sine of that, and that equals 0.5. I'm just going to multiply that times 1, that gives me 0.5. So the 0.5 is equal to 1.33 times the sine of theta R. Now I need to get theta R by itself. So first I want to divide both sides by 1.33. And what that's going to do is going to make my sine of theta R is going to be equal to 0.5 divided by 1.33. So I take 0.5 divided by 1.33. And that gives me 0.375. Now I can round these numbers to 2 decimal places. Your answer, if you round or not when you work these, might be slightly different than my answers, but as long as they're within a few tenths of that, that's fine. So this round 2 decimal places is going to be 0.38. Now when I get to this point, I need to solve for theta R. This is how I do that. I would take theta R equals, and to get the sine, rid of the sine, if I move it to the other side, it's going to make it the inverse sine. So it'd be the inverse sine of 0.38. So I'm going to take 0.38, and then I'm going to take the inverse sine. That's that sine -1 part on your calculator. So I do that, it gives me 22.33. I can round these angles to whole numbers since it's an angle. So theta R is going to be equal to 22 degrees. So what this says is if the light wave enters, leaves air and enters water at an angle of 30 degrees, it's going to bend and refract at an angle of 22 degrees. And actually air enters water, it's going to slow down and it's going to bend towards the normal. If that would have been the other way around, and it was water and entered air, that refracted angle would have been larger than the angle of incidence. That's one way you can check it. Since it's going to be, light's going to be slowing down in this situation, the angle of refraction should be less than the angle of incidence. Okay, our next problem says a light wave leaving water enters fused quartz. So water that's leaving water, I'm going to let you know water is going to be my first medium. So that's going to be my first one. Quartz is going to be my second medium. And it leaves a refracted angle of 60 degrees. And determine the angle of incidence. So to write down my givens, it's leaving water. I need to know the N1 value. That's going to be my N1 for water. And that was in the last example. It told me it was 1.33. N2 is going to be 1.46 for quartz. It's higher because, this light's going to slow down. It's more dense. And it tells me that my angle of refraction, my theta R, is equal to 60 degrees. And determine the angle of incidence. I'm looking for theta I. Next, my equation I'm going to use Snell's law, N1 sine of times the sine of theta I. You can put parentheses there to make you know that you're multiplying. Equals N2 times the sine of theta R. I'm going to substitute and solve. So I'll put in for M1 is 1.33, and I'm going to multiply by the sine. My unknown is my theta I. Equals N2 is 1.46, and that's multiplied by the sine of 60 degrees. So then I'm going to do the right side. This is going to be 1.33 times the sine of theta I equals, and then if I take 60 and do the sine of that, it gives me that number, and I'm going to multiply by 1.46. Gives me 1.264. I'm going to round this to two decimal places, 1.26. Alright, now I want to get rid of this 1.33, so this will be the sine of theta I equals 1.26 divided by 1.33. And I'm going to be left with, so then it will be the sine of theta I equals, so I'm going to take 1.26 divided by 1.33. That gives me 0.947. Round that to two decimal places. That's going to be 0.95. And then I need to solve for theta I. So I need to get rid of that sine. When I bring it to the other side, it's going to become the inverse sine. And then it's 0.95. So I'm going to take 0.95 and do the inverse sine. And it gives you 71.8. Round that to one decimal place. So theta I is going to be equal to 72 degrees. And then we can kind of see if this makes sense or not. It's leaving water entering diffuse quartz, so it's going to slow down. When it slows down, the light is going to bend towards the normal. Oh, actually the angle incidence is going to bend, so the angle bends towards the normal, so the angle of refraction should be less than the angle of incidence, and that's the case. 72 is greater than 60 degrees. All right, so to look at our next one, this time it says a light wave leaves the air, so air is going to be my first medium, at an angle of incidence of 42 degrees and enters an unknown material, so that's going to be my second medium, at an angle of refraction of 25 degrees. Determine the index of refraction of the unknown material. Since the unknown material is my second medium, I'm going to be looking for N2. So I'm going to write down my givens, my unknown. It says first in the problem that my angle of incidence is 42 degrees. And then my angle of refraction is 25 degrees. And air was my first medium. So N1, normally I would give you that number, but air has already been used in a previous problem and it told me air was 1.00. And then I'm looking for N2. Next, I'm going to write my equation. It's N1 sine times the sine of theta I equals N2 times the sine of theta R. Now I'm going to substitute and solve. So N1 is 1.00 times the sine of 42 degrees equals N2 is my unknown, and that's times the sine of theta R, which is 25 degrees. So now to kind of shorten this up, I'm going to take 42 degrees first, take the sine of it, equals that, and then multiply it by 1. It's just going to be 0.669. And I'm going, I round that to 2 decimal places, so that's going to be 0.67 equals, and that's going to be N2 times the sine of 25. So if I take 25 and I take the sine of that, that's going to equal 0.4226. So I'm going to round to 2 decimal places, that'd be 0.42. Now to solve for N2, in this case I'll need to divide both sides by 0.42. So my N2 is going to be 0.67 divided by 0.42. It's 1.59. Round this 2 decimal places, that would be 1.595, and now I'll round up, so it's going to be 1.60. This doesn't have any units for the index of refraction. And if you get a number between 0 and 3, that's good. If you get something over 3, because most of those values, like diamond is probably at the highest value at 2.42. So if you get anything over, that number or 3 especially, then you've done something wrong on these problems. Okay, so to look at one more, it asks me, what is the index of refraction of a refracted medium if the angle of incidence in air is telling me air is 37 degrees, so it's telling me the angle of incidence is 30 degrees and the angle of refraction is 20 degrees. Well, what's my first medium and what's my second medium? Well, my first medium is telling me, if it tells me that the angle of incidence in air, and it's giving me the angle of incidence 37 degrees air, then it's telling me that air is my first medium. And if it asks me what's my index of refraction of the refracted medium, well, it's telling you that is your second medium. So when I start to write down my givens and my unknown, it's telling me that my N1 is going to be for air, and again that value is 1.00, and my angle of incidence is 37 degrees, and my angle of refraction is 20 degrees, and I'm looking for N2, which is going to be the N value, the index of refraction for that refractive medium. Alright, and I'm going to write my equation. That's M1 times the sine of theta I equals N2 times the sine of theta R. I'm going to substitute and solve. N1, that will be 1.00. Multiply that by the sine of 37 degrees equals N2 is what I'm solving for, and that's times the sine of theta R, which is 20 degrees. So now I'll take the 37 degrees equals that, and then multiply it by 1. It's just going to be the same number. Around this 2 decimal places, 0.6 times 60 equals, and this is going to be N2, and then I can do the sine of 20. I'll take 20, take the sine of that, it equals 0.342, around the 2 decimal places, that'd be 0.34. Now when I get to this point, to solve for N2, I just want to divide both sides by 0.34. So N2, when I take that, will be 0.6 divided by 0.34, and that gives me 1.76 around 2 decimal places. That would be 1.76, and it has no units. And all these problems will work like this. Now most of them are going to be straightforward, like number 1 and 2. Sometimes you'll have to kind of read it to make sure you know what you're solving for. Now your assignment is to do this worksheet. Now in the problems I did not give you the N values, but they're in this table, this chart at the top here, the N values that you will need. Now if you look at some of these, you'll just kind of have to read the problem carefully to decide what's your first and second medium. For example, the first one, light ray traveling from air to crown glass. Well, air is going to be your first one, and crown glass can be your second medium. Number 2 is worked just like the one we just worked. Number 3 is like that one also. And like number 4 is the same way. Air, is your first medium because it's relating air with the angle of incidence. And then like number 5, it says it's traveling through air and then it strikes water. So air will be your first medium, water will be your second one. And I think all the rest of them are pretty easy. Now number 9, it's going to ask you to solve for the first part of it. It's asking you to solve for the index of refraction of your second medium, and then what's the second medium based on the N value. Once you calculate the N value for number 9, just look back at the chart, first the worksheet, and figure out what medium it was based on the N value.